Swayam Prabha. Digital India. Educated India.
Friends, today we shall be again continuing with our earlier topic, that is the gradually varied flow. Well, we were discussing about computation of gradually varied flow, and under that topic we were discussing that different methods of computation, and we were talking about numerical methods also. And today we will be going to some extent into deeper of these numerical methods, of course not in detail, but still we will be covering some of the aspect of that, and then we shall be taking up some of the hands-on, say some of the numerical problem that can help us in understanding the method we have discussed in a better way. Well, with that thinking, let us see what we did in our last class. That is, we have discussed, just to summarize till now what we have done, we have discussed the classification of gradually varied flow. That way we know that there are different classes. Then we did discuss about the characteristic of gradually varied flow, different type of profile, how they form and what are their characteristic, at upstream what happened, at downstream what happened, and whether the profile is horizontal, whether it is rising or whether it is falling, that sort of things we have discussed, and that very basic knowledge is important for computation. And then we did discuss about the influence of control section, that is, if the profile is forming in a subcritical zone, then we could see that control is at downstream. If the profile is forming at supercritical zone, then the control is at upstream. So those aspects we did discuss, and of course in the last class we again did discuss about the formation of profile over series of channels, rather say channels which we can consider as series of channel of different slopes. Say slope is changing from mild to milder, milder to steeper. So that sort of things we did discuss. And of course, while discussing those things, we did not consider a slope change which can lead to another phenomenon called hydraulic jump, because we are yet to study that one. Then after that we went for computation of gradually varied flow, and in computation of gradually varied flow, just to recall, we studied particularly two methods. One is the direct step method, and the second one is the standard step method. Well, and of course there are some methods like graphical method, then direct integration method. So these sort of methods are there which need recourse to graph and which need recourse to say tables and charts. So as now in the days of computer we do not like to go for those things, or rather we have other alternative way, or say we can develop a computer program to solve this program very easily, and that's why we are not using those methods, and that's why we are not discussing those methods here. Here what we are discussing is standard step method, then direct step method, and of course we will be discussing numerical methods. And in numerical method, as said earlier, there are several numerical methods which can solve this sort of governing equation. This sort of governing equation means the governing equation of gradually varied flow, which is of the form that dy dx is equal to, it is a function of x and y. Of course, when it is a non-prismatic channel, then only it is becoming a function of x, otherwise it is a function of y only. But it is not a function of x only, and that is why we cannot solve it by analytical procedure, and because this is a non-linear differential equation. So, this non-linear differential equation, for solution of that we need to take recourse to different methods, and these are, say, one is direct step method, one is or the standard step method, then we need to discuss about numerical methods. Okay. So, let us now discuss on these numerical methods. Of course, we have discussed on direct step method already and standard step method, and we will be taking up some numerical problem for solving this standard step method here, just to have a feel of the actual problem. Well, so for numerical methods are concerned, in fact, there are several numerical methods that we did discuss in the last class for solving this sort of equation, that is dy dx is equal to, rather in not writing the directly governing equation gradually varied flow, if it is f x y, and for solving this sort of equation we have different type of numerical methods, and here we are discussing only a few of those methods, and we are not discussing more details of those methods, but just to understand how basically the concept of numerical applications are applied, we will be explaining that with the help of some graphical representation. So we are taking up the first one, this is Euler's method. Say what basically the numerical methods do. To see that, suppose we have a curve, it may be gradually varied flow, it may be anything. Well, now this curve has a equation like this, dy dx is equal to f of x y, it is a function of x y. In our case, this equation is dy dx is equal to, say, sb minus sf divided by 1 minus q square t by g a q. Okay. Well, in case of gradually varied flow, otherwise it can be any equation. Well, now if we just know the initial value, suppose in this direction we are having y, in this direction we are having x. Well, if we know the initial value at x equal to 0, then say this is equal to y 0, suppose at x equal to 0 we know the initial value of the y. Then for this sort of situation, which we can call that initial value problem, we know this initial value and then we need to solve for the other value, then this method is quite advantageous. How? Say when we know the initial value y 0 and we have an expression, and of course this is at x 0, that also we know, and we have an expression for the slope dy dx. So, if we put this value y 0 and x equal to, say, x 0, I will not write the 0, at x equal to x 0, this can be any value also, it can have any value, not necessarily 0. Okay. So, at equal to x 0, so we know this value. So, if we put this y 0 and x 0, then we get the dy dx at x equal to 0 and x equal to x 0 and y equal to y 0. So, that way this value is known. What is dy dx? It is nothing but the slope at this point. If I draw the tangent to this point, then of course my line is becoming almost horizontal because there should be some slope in this. Let me take the curve like this. Okay. So, say at this point if I draw a slope, it is going like that, and this slope is nothing but a tan of this slope rather is called dy dx, tan theta we can write. Okay. Now, in numerical method, what is that? We know this value, and then if we take a small distance in x direction, if we take a small distance in x direction, okay, I am taking it here, I am taking it here. Say this is a very small distance delta x, okay, or in many numerical method it is written as h, a small distance h. Okay. Now, so what about this distance? As we know, this slope dy dx, and if we write this distance as delta y and this is delta x, then we can write that tan theta is nothing but delta y by delta x, or we can write that dy dx at say point y is equal to y0, x equal to x0, this is equal to say delta y by delta x. Well, so from this we can find out what is delta y. So, delta y is nothing but delta x into say dy dx at say point x0 y0. Well, so by the simple expression we can find out delta y, and this is a horizontal line we are drawing. So, up to this much distance, this distance is nothing but y0. Well, now the distance y0 plus delta y will give us up to this particular point. So, now if I just draw it in an enlarged form, then I can show that y0, which is the point, actually we are interested to know that at x equal to x1 means say delta x is what? Delta x is nothing but x1 minus x0. At x equal to x1, what is the y? So, our actual value for y1 is this much, Our actual value for y1 is this much as per this curve. But if this delta x is very small, then we can write that delta x is equal to y0 plus delta y approximately equal to we can call. Now, of course, from this curve it is not it is quite visible that y1 and y0 plus delta y, these are not equal. But if I consider my delta x to be very small, now you can see, suppose my delta x is here, this is my very small delta x, If my delta x is only this much, then with this being our delta x, then say this will be small distance will be delta y, this small distance will be small delta y, say, and then you can see these 2 points, that is the point of the curve and point on the tangent, are almost at the same point. Well, so this delta x being very small, we can very well write that the delta x, sorry, this is not delta x, we should have written it y1 is equal to y0 plus delta y, that we can write very well now. So, this is our y1, and we can write that y1 is equal to y0 plus this small delta. This is valid for a small value of delta x, but if we increase our delta x to larger value, then this is introducing some error. Now, once we get the y1, then this y1 become our known value. Then we can take a slope at this point. Suppose y1 is known. Well, let me just take it. If y1 is known, then we can find y2 is equal to, when y1 is known, you can find out the slope, say again delta x, say next delta x, you are taking delta x into say dy dx at y1 x1. So, this value dy dx you can calculate at y1 x1, as now you know x1 value and y1 value. Knowing the y1 and x1, you can calculate dy dx, then multiply this by delta x, and you can get your next y2. That way you can continue solving for values of depth y for different x. But from this graphical diagram or from this graphical representation, one point is very clear, that if our delta x is not very small, then if our delta x is not very small, then we can end up in getting, suppose our actual curve is like this, and with our numerical value we can have, suppose this point, if we consider is this point, then this point we can get suppose here. Then you are calculating based on this y1 value, say for this x1, x2, x3, like that we are calculating, and for this value if you calculate the slope again, say you are getting this value first, then at this point you are taking slope, and then you are getting another value here, and at this point you are taking slope, and then you are getting another value here. So, your curve will be like this. It is basically some discrete point you are getting, and your actual curve is this one, and but your computed curve will be this one. This will be your computed, and this will be your actual. So, that way you can always end up introducing some amount of error. If the curvature is in the downward side, the things will be in the opposite direction. It will be little away towards upward direction. So, that is, though it is very simple Euler's method, but it can have some amount of error, provided your delta x is not very small. Again, not very small is quite blurred, that what we mean by very small, that is also we need to see into that particular aspect. Well, then because of this particular drawback, this was improved based on some of the consideration that is called as improved Euler method. Well, so this is our graph, and now we can see, say if with dy dx at this point we are getting slope at this point, and then we are, suppose our delta x is this one, I am drawing a large delta x, okay, and then for this delta x, say my delta y initially calculated will be this one, delta y, okay. And this being y0, this is y0, and from here to here it will be y1, that is y1 is equal to y0 plus delta y. Okay. Well, now we can see that if we take again with this known value y1, if we take a slope, this slope at this point, or rather for this y1 value, the slope will be like this, Now, based on this slope, if we calculate, suppose this slope we are considering that this slope is not there, rather here, then if we calculate, okay, let me draw the slope here. If we calculate here, then our let me take the slope like this. If I draw the slope here, then it will be going in this part. So, based on this slope at the point y1 and y1, if we calculate our delta y, then delta y will be large like this. This is say delta y we are calculating based on the slope at this point, but slope we are using the slope at this point, but putting the slope at initial point y0. Okay. So, this time our y1 will be quite large like this. And now, if we take, say this is our y1 computed for the first time, and this is say y1 computed for the second time, and this is the delta y computed for the second time, this is delta y1 computed for the first time. The second time means with the on the basis of the slope taken at the value of y1 which we have computed. Okay. Now, if we do like that, then we are getting the value in different way. Now, if we take average of these two value, that is average of y1 computed with this level and y1 computed with the first one, then if we take average, the value will be coming somewhere here, and you can see very well, that is average of this means your depth is neither this one and this one, you are getting average, this is your y1, and that average y1 is you can write this average y1 is equal to say y0 plus delta y1 plus delta y1, this is y11. Okay, let me write little larger here, say delta y11 plus delta y12 divided by 2. Well, so that way we are getting this expression. And what is this delta y1? That is nothing but, we have already explained what that delta y1, that is nothing but delta x into dy dx. So, what we can write here, say y1 is equal to y0 plus delta x into, say or you can write delta x by 2, or you can write half of dy dx at say point 0 and plus dy dx at point 1. Well, so this way we can compute the y1 value, and this y1 value will be more closer than the earlier one, Well, so this method is referred as improved Euler method. That means we are using the slope at the initial point, and then we compute the second point, and based on the slope at the second point, based on the known value of y1 in the second point, we again compute the slope, and then we take average of these two slope, and then we calculate this y1. And if the variation of this slope, see slope is changing, here it is this much, here it is this much, so slope is changing. Now, if the change of slope between this point and that point is linearly if the slope is changing, then this method will give accurate result. But of course, the curves are not like that, that the slope will be changing linearly, and it may not be this for all situation, and that is why it will not give you that accurate result. And of course, this method, after this method, this has another advantage now. So, what we have seen, we are taking average of this slope, average of these two slope, and so once we calculate this y1, and say once we calculate this y0, okay, y0, and then we have calculated the y1, and then we want to calculate y2, rather than again doing like that, taking a slope here and then taking a slope at this point, and taking half, rather than doing all those things, what we can do, that for computing this value, we can see that if we use the slope at this point, that is at the middle point, and then if we calculate from the beginning of this one using the slope at the middle point, we are reaching much nearer to the value of the second point. If we consider this as 0, then this is becoming the 2. Second means that it is actually the third point. Nomenclature is becoming as y2. So, what we can do, y2 is equal to, we can write y0 plus, we are using this time our delta x is 2 delta x, twice of delta x, into slope we are using dy dx at say y1. So, to calculate the value of y2, we are using y0 and twice delta x, then dy dx at y1. And in general, if we want to write this, in general we can write that y, say if this is I plus 1, we are interested to find I plus 1, I minus 1 is also known to us. So, what we can do, that for calculating I plus 1, we can write y I plus 1 is equal to y I minus 1 plus 2 into delta x into, we can write this as y dash. Y dash means, y dash represents a dy dx at I equal to 1. Dy dx at the point I, middle point. So, this procedure can be adopted. This is basically, the concept is similar to this one. Rather than taking average, we are using the slope